Let's figure I better record this. So we get a total of 2.553 amps. So I bleeder is equal to 10% of this 2.553. So I bleeder comes out to be 255.303 milliamps. Now on that one I shortened it out just because that's what my calculator automatically did for me. But using those previous values, this is all it showed, but it still had the rest of the values stored in the memory. iLoad is going to be the load currents for whichever one has the highest load, the highest draw. So in this case, we've got the 2.25 and the 303 milliamps. Those give us 2.553, whereas down here we get about 1.6 amps total. So we're going to base it off of the larger of the two load currents. Yeah, and then we take 10% of that total load current. Yes? Because of the ground. If the ground wasn't there, this wouldn't work this way. We would have, it would change how a lot of these interactions and currents are going to flow. That answer your question, Reed? Okay. So we have our bleeder current. And we've already determined that it's the top portion. So our bleed current is going to be right here. So 255.303 milliamps going up in that direction. So now we're going to come back and we're just going to start analyzing these different nodes. I like to start over here, but some people like to start here at this node and kind of work the other direction as well. It doesn't really matter which way. You have to start somewhere that you're only missing one current coming in or out of that node. So let's look here. So we're going to look at node A. So we have 2.25 amps leaving the node. We have 1.296 amps coming into the node, and that's it. So we have one other connection. First of all, which direction is this current going to be going? In or out? Into the node. It could if this current dropped below this guy. So we've got the current flowing in that direction. How much current do we have? Milliamps, yep. So we have to have 954 milliamps going into that node to be able to match up to the 2.25 that we have. So at this node here, we have 2.25 leaving. We have 1.296 going in. So we're short 954 milliamps coming into this node. Okay, so then we're going to come back to this node because now at this point we're only missing one value. We'll call this node B. So I have 303.03 milliamps leaving the node. I have 954 milliamps leaving that node. And I have 243.902 milliamps going into that node. So where am I short? Do I have more current going out or more current coming in? More going out. So I have to have more current coming in. And again, that difference is the sum of all of these guys. So we take the 954 milli and the 303 milli, we add those together, and we subtract out the 243. So we can get these to equal. And when we do that, we end up with 1.013 amps. So now, when we look at this node, if we were to take 1.013, add it to the 243, that's going to give us how much? So we have 1.25 amps going in. We have 954 going out and 303 going out. That's going to add up to the total. So another way to look at this. So at node A, so we'll go back a step. We got 1.296 amps going in. We have 2.25 amps going out. And we have one more node, or one more connection going into that node. So we have to have enough current coming into this node to equal what's going out. And that's where we had the 954 going in. Then when we get to node B, again, we've got 954 milliamps going out. We have 303 going out. And we have a total bless you, coming in. And we have one more leg that we have to determine what current. So to get these guys to be equal, so this gives us a total of 1.257 amps going out. And we only have 243 milliamps coming in. So to get these guys to be equal, how much current we have going out versus how much current we have going in, this is where we have the additional 1.013 amps coming in. Does that make sense? Where you lost? Okay, so do you get where we're going from? Like what we're looking at? Okay. So what part on this one are we lost at?
I do a bit better with when I can see everything laid out step by step.
Okay, well that's why I'm labeling these as A and B. That's our roadmap. So the first thing is we have to look at this node because we have 2 out of the 3, we can solve it. That gives us this section here. Now we have 3 out of the 4, we can solve this one. The only other place we could go is up here because we have 2 out of the 3 going in. This guy we're still missing a couple, but now that we found this one, we'll have it. So the next step, like I said, we want to look at where do I have the information to solve where these are at? Because we know that they have to be equal, the currents have to be equal, the going into a node and going out of a node. So we're going to move over here to connection C. So at point C, we have 4 connections. We have the ground, which we're not going to have any current flow, so we don't have to worry about him. We have 3 connections. We have 255.303 milli going out. We have 1.013 amps also going out. And we have one more connection to match the current going in as what's required to go out. So with this one, since we only have the one connection, we're going to simply add our outs together. And this gives us 1.266 milliamps. So I know coming into this node right here at point C, I have to have 1.266 milliamps coming into it. Sorry, 1.26 amps. So in this case, the bleeder current was on R3. This one would actually be flipped around. Yep, it'd be going in. Because we have to have, the bleeder current here has to go somewhere. And if this has current that's coming up through here and then turning this direction, this isn't bleeder current because it has current for the load that runs through it. Bleeder current never touches the load. So all we're doing is we have a total amount of current moving through the circuit and we're just rerouting it different directions. That's all we're doing. Basically, when we analyze that node, what do we have to have? Is it current coming in or current leaving? And so in this case, we had to have more current coming into this node, so it's going to be pulling that direction. Correct. So node B, again, is deficient in current because we're trying to send out more than what we have coming in. So we have to have more current coming into B, and that's where this value comes from. So now that we have C, the only branch we have is to come in, so we're going to have a total of 1.266 amps that has to be fed into node C for us to be able to spit out what's required of it. So one way to think is we're starting at the end of the problem, looking at what we need, and then working backwards to figure out how do I get that to my load. So we have 1.266 amps going through our R3. Then we'll come down here to this point. We know leaving this node, slide this up a little bit. So at node D, we have current leaving, based on what we've already established. So I have 1.266 amps that's going out. I have 243 milliamps that's also going out. How many connections do I have coming into this node? 3. So I know 2 of them. I'm missing the third. So in this guy, I'm missing the current coming into that node. So since it's the only one, I just add these guys together to get them to be equal. That's all we're trying to do is get our nodes to be equal. So we take the 1.266, we add the 243 milliamps. So we have 1.51 amps running through this guy. So now we have a choice. We can finish out here, or we can even jump up and do the connections between R1, R2, and the rest of the circuit. I like to just finish out the direction I'm going. So at node E, again, I have 1.51 amps leaving this node. I have 1.29 amps going this direction through our load D, which means I have to have current coming into this node to supply those. So at node E, I have 1.51 amps going out. I have 1.296 amps going out, which leaves me to fill how much current is going into this node. Which is 2.806 amps. So now that we've established this guy, one of the things this gives us is one of our checks to look for. So at this point, we have 2.806 amps running through R5. And what is the current that's running through R5? Current total. So one of the things, where else do we have our current total? On the top. So leaving that value alone, we're going to check to see if we have our values added up correctly. So I'm going to jump up here because I want to find this, I want to solve for this node, but we're missing 2 branches. So here, I'm going to jump up to this node. This is going to be node F. Coming into F and going out of F, what do we have? We've got the 303 milliamps, and we have the 255 milliamps. So at F, we have 255.303 milli, and that's coming in. We have 303.03 milli. That's also coming in. And the only other branch we have has to be going out. So when we do this, we have a total of 558.333 milliamps. So when we come back up in here, we'll plug in the 558.333. And now I can do my last node. So this is going to be my final check. If I've done all these correctly, I should get 2.806 coming out, because both of these currents should be the same. So again, coming into point G, I have the current coming from load A over to it. So I have a 2.25 amps coming in. I have the 558 milliamps coming in. So coming out of G, I only have one more line, so I have to have equal amounts going out as I do coming in. And so when I add those guys together, I get 2.808. So I got 2.808, and down here I got 2.806. For all intents and purposes, that is close enough. That's just rounding, which in some of these areas over here, my calculator cut those off. So all we've done, like what Kately said when she was working on these, it's the map of me traveling around between all the different points, dropping off stuff and picking stuff up in class. That's all we're trying to do. We're just trying to figure out how much current is getting moved between these connection points. It's a little bit weird because when we're looking at these, this guy right here and this guy right here, we will never actually measure. We will never measure them because there's no reason to. Plus there's no connection there. Usually this is just a single piece of wire or a connection point on your breadboard. So you have that much current flowing through the breadboard to the other components. We could go through and build it to measure that, but with those we'll never see those. But this is how the current has to flow for this thing to work correctly. And again, the biggest thing here is if we measure our voltage, we measure this guy, if those two are correct, our circuit will be correct. So with that, we now have our currents, we now have our voltages. Now we can just use Ohm's law to solve for the resistance values. All right, so Carson, go ahead and do R1. Fallon, do R2. Jessica, do R3. Morgan, do R4. And Max, do R5. So these guys, so what these guys are doing really is we have two voltage dividers that we're worrying about. We have an upper one and a lower one. And the only interaction that comes through is across these connections here. So when we go back here in a second, we'll do a loaded voltage divider. We're only going to be doing half of this guy. We'll simplify it down again. Okay, so Carson, what'd you get? Okay, Fallon? Jessica? Okay. Morgan?
I got 9.94.
And Max?
356.125.
I know, that's what I'm trying to understand.
There's Dylan here today who's taking your test. About every single question is wrong, except for the ohms over voltage, you got right.
Yeah, that's weird.
My problem was, is for whatever reason, so like the Buddhism was on the bottom, I had the kind of see of me going out. And it should be on the bottom.
Should be.
That was my problem.
So really, the way to tackle these guys is, because there's a big convoluted mess. There's a lot of stuff going on. There's lots of moving parts. Look at the problem and say, okay, where do I need to start? Where can I start, really? You know, so we're looking through, and then the tools that we have so far, we have Ohm's law, we have Watt's law, we have Kirchhoff's voltage law, we have Kirchhoff's current law. That's primarily what we solve with this guy, is using Kirchhoff's current law. We've also got the rules for parallel circuits. We've got the rules for series circuits, which we used our parallel laws to solve for the voltages. We used our series laws to solve for this voltage. And then we have to switch into Kirchhoff's current law to be able to solve for the rest of this guy. So the next part is when I'm going through and solving one of these circuits, again, you look at what information do I have and what information am I missing. So right off the bat, again, we'll kind of walk through this again step by step. We have a connection here with 3 points. We know a value here. We know a value here. We don't know the third leg. There's a good place to start. We have 2 out of the 3 missing or unknown values. We look at this node here. We have 1 value coming in. We don't have another value, and we don't have another value. So we're missing 2 out of the 3. Not a very good place for us to try and start and work through this. This guy down here, we're missing 2 out of the 4. This one over here, we have 1 coming out, but we're missing the other 2. This node, we have 1 value, we're missing 2. And then same with this guy, we have 1 value and missing 2. So when we're looking at these, we really only have 2 places that we could start. We could start here at this guy where we're missing just this branch current, or we can start here where we're just missing this branch current because of our I bleeder was on this resistor. Now if our I bleeder was down here, we would start at this point because we know the current going this direction, we know that bleeder current, we can calculate from D to E. Okay, so now we have this guy. Let's take a step back and look at half of one of these guys. Let's simplify this down a little bit. Come on. All right, so we have, yes, I do like this one. So our voltage total is 78 volts. Our load A is 78 volts at, what we got? 16.596 amps. It is a lot of amperage. VLB is 68 volts. So RLB is 68 volts at 61.818 amps. So again, as we go through this guy, we're going to use all the different laws that we have. So using our parallel laws, what are the voltages of R1 and R2? R1's 10 volts because R2 is 68 volts. This guy and this guy, if we were to connect straight through, are in parallel directly with our 78 volt source. So that voltage has to split up between those two. And then because these guys are in parallel, that's where we get how they split up. We don't have any series component because we don't have a shunt resistor. So we don't have to do that. So now we're going to get into Kirchhoff's current law. So again, the first thing we want to do when we're solving these is figure out which currents do we know are going to flow. So using, like I said, using either electron flow or conventional current flow, we're going to have the current mark out the direction. So I'm going to use electron current flow, which has the current flowing from where to where? Negative to positive. So my current, really, is going to come this direction. It's going to split and go up this direction. This current is still trying to get back to the positive, so it's going to cut across. We know the current, when it hits this node, is going to split again. We're going to go that direction. Do we have all of our connections, all of our pathways with some sort of at least a current direction flow? These ones are a lot easier for that because we don't have another section down here that is forcing the current one way or the other. So when we go through this, we have a lot fewer connection points. We've got one here, we've got one here, and one here. So looking at them, this point up here, how many knowns and unknowns do we have? We've got one unknown, two unknowns and one known. You want to separate that because there will be two different currents. That's the other way when you're drawing these guys. If you make a continuous line, so it's going to be that same current, that whole path, because all that's still in series. We want to split up our arrows when we have different segments. So we have two unknowns and one known. What about this node? How many connection points do we have? 3. We have one known and two unknowns, so we can't start there. Come down to this node, what do we have? 3 unknowns. We have no idea what's going on at that node. Okay? When we come here, what do we have? 1 unknown and 2 knowns. So there again, there's our place that we can start. The only question is, we do have another current that we didn't put up there. Our bleeder current. So the current total for the load, what's our load total current? And we get that by adding together the two load currents that we have. I bleed is equal to 10% of that. So that's how much current we have for our bleeder. Now, where does our bleeder current go? R1 or R2? Why? Yeah, as it comes up through here, it's never going to hit into the load. So I bleed is here at 7.8414 amps. So now, if we were to go through that, we have enough information to solve at this point, and we have enough information to solve at this point. Do what? Correct. Yep, in this case, IR2 and iBleeder are one and the same. So just like we did before, we can start at either one of these points. We'll start down here at point A. So remembering, this is where Kirchhoff's current law comes into play. Current going into a node must equal current going out of a node. So we have, at point A, we have 16.956 amps going out, and we have 61.818 amps going out. How much current do we have, and what direction is it coming into at point A? We've got 78.414 going out. So how much current do we have to have going into that node? 78, because they have to be equal. We've got 16.956 out, 61.818 has to be equal to the current coming in, and in this case we're solving for an unknown variable. So this current is the 78.414 amps. Let's look at it in just terms of just a straight math problem, okay? The next step we can come to is we can move back a node. Because again, we have two values coming out of the node and only one other path coming in. So for these guys to be equal, what currents do I have at node B? So we've got out and in. Yes. Yeah, this is 78 right here. I forget that the decimal points are hard to see when you back up. I can see them when I'm up close and personal. So if you don't see the decimal points, please let me know. I try to make them bigger so you can see them.
What line is that? It becomes 78.
Right, this one? Because over here we have these two currents leaving, and they have to be equal to the currents coming in. So just with just a simple math problem here, we have 19.956 going out, 61.818 going out. We can add those guys together to get a total out. They have to be equal to the total amount of current coming in. So in this case, it has to be 78.414. Then at this node, again, we've got the 78.414 going out. We have 7.8414 going out. Those the in and the out have to be equal. So at this point, we put in our unknown, we solve for it, and the current that we have to have coming into this node big excessive, yes. That's also the total current. So all we're doing is we're just finding the currents coming in and out of each individual leg. Okay, so now, oh my gosh. So now we're going to find into the next step. We can either go, well, the only other option we have is to go here, because here we're still missing 2 out of the 3. This one we have 1 unknown. So we'll jump up to this guy, to where we have the information to solve for. The current at point C, we've got current going out, current coming in. What currents do we have coming out of point C? Yep. We don't have one yet. We have one, but we haven't solved for it. So that's our unknown. Okay? The current we have coming in is going to be the current coming up this way and the current coming this way. So we have the 7.8414 and 61.818. $695? Okay. So to get these things to be equal, we have to have this much current coming out of that node to maintain. So now we have this current up here. And we can solve for this last current. Again, keeping in mind, what current is this? Total current. What current's this? Total current. So when we add these guys together, we should get this exact same value within a couple of tenths of, depending on how we round it. So at point D, do what? 659? Okay, so we know coming in and out at point D, we know we have the 69.695 coming into it because we just solved for that value. What else do we have coming in, coming out of that node? We've got this 16.956 coming into this point as well. How much do we have coming out? The total current. So we've got this coming in, we have this coming in. We have to solve for how much is coming out. That's the one variable we don't know. So coming out, we don't know. We will add this to the 16.956 amps. And when we add those two together, what'd you say? A little off. But again, we're 400 milliamps off of 86 amps. So we're let's see. Yeah, we're at 0.465%. So yes, we did lose some, but again, that's rounding values off. That can cause you a problem later on. If you're rounding off too far too early, by the time you get to the end of it, you're going to run out of accuracy to be able to be right. So now, we're going to come back and look. Do we have all the currents that we need to solve for the unknowns at this point? We do. We have a current coming through R1, and we have a current coming through R2. We really could have stopped before we did the value on D, but again, I like to do that. That's one of my double checks, is because I have 2 points independent of each other, more or less, to where I can double check these values. This value is key. I should have this value coming out. So, like I said, it doesn't take any extra time to really run through one more addition problem and make sure that I have the value coming up right. Because again, it's a conservation law of energy. We can't create energy, we can't destroy it inside of this system. We can use it, convert it, do what? You've just created perpetual energy. But yeah, so we can't destroy it. So we have to be able to account for all the voltage and all the current and all the power going into and out of this system. This is supplying it. These guys are using it. So when we come to the end, we can solve for these values for R1. So R1 is going to be 10 volts divided by the 69.659 amps. And R2 is going to be 68 volts divided by the 7.8414 amps. Let's see where we were. Dylan, R1, and Reed, R2. And in the quiz, what it's looking for is this answer and the resistance values. What'd you get, Dylan? Just amps. We haven't hit kiloamps yet. How much did you have? Okay. And then Reed, R2. That's what I got. Now we could go and build this circuit. If we had components that could handle the power, we could build this circuit. And test it. I mean, wouldn't that be fun? 70 amps running through it. We could. Yes.
So 143 milliohms of resistance, that's a couple of feet of wire.
Mm-hmm.
Are there actual resistors that go that small? Or?
They do have them. They're about this big around, and it's literally a big piece of wire at that point.
I was so confused when I got that answer. I'm like, this game.
Yeah, real life application, probably not going to see something like this. You know, to the other stuff that we were seeing, even something like this is very acceptable, very believable. Okay? We have lots of devices that run on several amps of power. Cell phone chargers are between 2 and 5 amps. That's how much they run to charge your phone. Motors are going to be drawing that much current all the time. Hair dryers, curling irons, that kind of stuff, we're dealing with the amp range. Those ones are 120 volts and, 10 amps, things like that. Heaters are another one. Heaters draw a lot of current because they're converting that current into infrared energy, which then gets translated into heat. Heaters are an interesting beast by themselves because of that fact. Is you lose some of that energy because it gets transferred out of the system. Because it turns into heat. Okay, so with that, let's go ahead and go to break. I'll pull up a troubleshooting question, and then we'll get to our series parallel with potentiometer, and then any other questions you guys have as we come through.
So I tried a bipolar problem on my own, and I somehow got everything wrong again. It's just a talent of mine.
I thought I went through and changed. I'll double check. They very well could have been from a year ago again. Okay, let's see. So you're off by a power of 10. So your bleeder current.
Well, I think I did everything right because 8.53, and then I got here's 510 and here's 77. So that's about the same top and bottom. So I think I did the process right. I think I just got.
That's what it looks like because like I said, it looks like a power of 10 off because you got 29.4 there. Yeah, because you have 216 there and 277 there, so you have 280 something, 294. So you put in here your load current is what you did on that one. Instead of your bleeder current, which is 10% of that guy.
Oh, that's what I forgot to do. Sorry, and I was also dealing with freaking microamps. I don't like dealing with microamps.
Microamps are rough. We don't use microamps a whole lot. You will, yeah. In real life, you will use microamps when it comes to transistors. Because it doesn't take a lot of current to control and change transistors how they operate.
We're determining if it doesn't hit the load or not. How do you do that with the current flow? I kind of get it over here because it doesn't interact with it at all.
Mm-hmm.
Is that what we're saying?
Yes.
Okay. This is just going in here and it's just going up like this.
Yeah. So then at this point you have load current as well. you have load current and bleeder current at that
Because it
point.
came from here.
hmm
Okay. Okay, and then you just pick the bigger,
The bigger
load?
current draw, yes.
So it'd be up here?
Yep.
Okay.
Yeah, so like on here, yeah, because we've got a total of the 2.553 amps up here, and down here we have about 1.5 milliamps or 1.5 amps. So we're going to take our bleeder off of this guy. And since we did it, we know it's going to go on one of these two resistors. And then when we look at it, you know, we know that we have the current here. We know the current's flowing this direction. So we know we can't have it here because this current's going to flow into it. So the only spot we really have is that resistor to our bleeder current.
Flow into it too?
Yeah.
For R1?
Not R1. You'll have the bleeder current and the load B current flows into R1.
Okay. Okay, I get it.
So another way to think of this is we have a finite number of something. You know, you could, you know, chocolate chips, chocolate milk, whatever, ice cream, and we're sending it to the different places. This is where we want to sample our ice cream because it's going to be pure. This stuff is going to run through the chocolate sauce, the caramel sauce, whatever it may be. We're looking for where we're going to find just the pure vanilla ice cream. The untainted current is one way to look at it as well. A lot of my examples come down to food.
Yeah.
So,
I enjoy that.
but really, to me, that makes a little bit more sense. Is we're looking for the untainted or unused current. Like that one? Untainted ice cream is our bleeder current.
I'm very confused.
I was comparing the current paths here to ice cream in a machine. So if we're making several different flavors, we're making 4 different flavors of ice cream. We want to find the sample of pure ice cream. It's going to be right here, because we're making chocolate ice cream, we're making strawberry ice cream, we're making, you know, any other kinds. Yeah, Rocky Road, things like that. This is going to be the only place that we have just a little bit of the pure left. Yes. Yes. This is where it is. Yes.
So like, would the current field like this way, like